Good morning. Today we're going to start the topic of filters. When we had talked about linear time invariant systems, if you remember back and we derived what a linear time invariant system can do to a signal, right? Specifically, remember if we put a cosine in, we saw that the system can change its amplitude and can change its phase, but the frequency will stay the same. Now, systems that are designed to specifically change the amplitude or change the phase in some way that we want to do are called filters. Now, the most common type of filters are things such as these. For example, let's start out with something called a low-pass filter. A low-pass filter is a filter that's designed, as the name implies, to be able to pass the low frequencies through the system, generally without changing them, and not letting the high frequencies through. So there's a difference, okay? So the high frequencies, we want to make the amplitude very little. The low frequencies, we generally want to leave the amplitude the same. Now, if we want to do that, what type of specifications would we have? Well, we'd have something that looks like this. We know that with digital filters, low frequencies are frequencies that are close to zero. High frequencies are frequencies that are close to pi. And so we know that all the frequencies are going to be between 0 and pi. Right, this is going to repeat because it's a digital system. Now, ideal filters, or filters that are not perfect, could pass certain frequencies without any change and then instantaneously jump to 0 and then not pass any frequencies above a certain point. Real systems can't do this. So real systems won't be perfectly flat here and won't be 0 in the range that we want to stop. And so they can change a little bit in this region, which we call the pass band. These are the frequencies that we want to pass through the system. It's not going to be 0 in this region, which we call the stop band, the frequencies that we want to take to 0. And since it can't jump instantaneously down to 0, we need some frequencies for it to go from a high amplitude to a low amplitude. And this is what we call the transition region. So we specify what our filter can do with something like this. There's going to be some region in here that we're going to let the amplitude of our filter be. Of course, this graph is going to be the specifications for the amplitude of the filter. The phase in this case is not going to be specified at all. It can actually be anything. So our filter, what would our actual filter look like? Well, to meet the specifications, the amplitude has to stay inside this region from 0 to omega p. From omega p to omega s, it can actually be anything. And then from omega s, we have to be attenuating. So the amplitude can't be up here, the amplitude has to be down here. And so this is what typically our specifications are going to look like. We're going to use this just because it's easier when we first start designing analog filters. You'll see why using this will make the problem a little easier. When we start designing FIR filters, we might want to look at the filters in this manner, or specify the filters like this. Now, a high-pass filter would do just the opposite. A high-pass filter would attenuate the low frequencies or make the amplitude smaller, and it's going to pass the frequencies that are high. Again, this is not 0, and we need some region for the filter to actually jump from 0 to 1. So we have a transition region and then the pass frequencies. Now, high pass and low pass filters might be the most common, but they're not the only kind. Right, we can also have filters that are called bandpass filters. In this type of filter, attenuates low frequencies, attenuates high frequencies, and just lets some band of frequencies through. So in this case we need to specify 2 pass frequencies and 2 stop frequencies. And there's also something called a band stop filter. It's not so common, but here we want to pass low frequencies, we want to pass high frequencies, but we want some band here in the middle to be attenuated. And so again we have 2 pass frequencies and 2 stop frequencies that are determined here.